So good afternoon again. I'm going to talk a bit about survival analysis as a machine learning problem. So I'm going to, so my talk is organized like this. I'm going to give an introduction to the survival analysis, what it is, and survival analysis comparing two samples. I think many people are working in clinical trials, so that will be important for them. Hazard function, then Cox proportional hazards model. This is what we have in the machine learning models that we're going to use. Then a sample survival analysis of prostate cancer. I've done it using a web resource. And then I'm going to go through what are the ML libraries available for performing survival analysis. And finally, I'm going to, if I have time, I'm going to do a sample survival analysis using Python and associated libraries. Now, before I proceed, I would just like to say that I'm not a statistics person, so there is quite a bit of statistics in this. So if there's something which may not be, I'm not that much into statistics, but just for the purpose of explaining this topic. So what's survival analysis, also known as time to event analysis? For example, you enroll people into a cohort, and then you study them over time in longitudinal analysis. So when they join the study from the time, and then you're going to studying for a period. So there are some events that may happen. The events could be exposures, could be death, and of course survival analysis is something that we use a lot in the health domain, but it's not necessarily only happening into the. We don't just use it into the health domain. It can be used in many other areas. Okay, so it's utilized in biology, in medicine, in engineering, in marketing, in social sciences, in behavioral sciences also. So the units of time in survival analysis range from days, weeks, months, years, and even decades, from the beginning of the follow-up till an event occurs until observation ceases. And that's when we say there's censoring. We're going to stop there. Now, some events of interest, like death of a person by any disease. For example, if you have enrolled cancer patients, and they have undergone some treatment, and then we're going to follow them to see how, if they again there's a recurrence of the disease, or after the treatment, how are they doing, or some of them may die. Or you have attrition of employees from organization. When employees join an organization, after how many years you can expect them to be leaving, okay? They might leave to go to other places. Or an incident of a natural calamity like earthquake or flood, or failure of machine tools. So as you can see, you can use that in many areas. But of course, we talk about it in the health domain. Okay, so survival analysis, actually, when we do that, we are talking about probabilities. So it's probability of an event occurrence after a certain time is called survival probability. Now, for instance, when we say that survival probability of a breast cancer patient surviving 7 years after undergoing mastectomy is 0.56, this means that the patient will survive at least 7 years after mastectomy, and there's a probability of 0.56 that she will keep surviving after 7 years. So similarly, there could be probability of 0.8 that she will survive after 3 years since mastectomy, and our reason is clear: within 3 years, chances of disease recurrence or metastasis is lower, and thus survival probability will be higher. So as you go, over time, the probability decreases. At the beginning, the probability is higher. As over time, it's going to decrease. A sample table for survival probabilities is like, for example, you have month, and then you have probability of survival. So you have for each month, after so many months for different patients, what is, the probability of survival. Now, since I work in the, in the area of cancer, so I'm interested into the survival analysis of cancer patients. So in many cancer studies, the main outcome on the assessment is the time of an event of interest. Now, there are different events of interest that could be there. So time survived from complete remission to relapse, a progression of the disease, or time from diagnosis to death. Now, at the end of follow-up, some of the individuals may not have the event of interest when your study is over, and thus their true time to event is unknown. I mean, you were studying the patients, it's over 5 years. So some of the patients didn't die or didn't have a recurrence to the disease, so you wouldn't know when they go out what's going to happen. So you don't know when an event occurred, whatever event you're studying. Now, survival data are rarely normally distributed, but they are skewed and comprise typically of many early events and relatively fewer late ones. It is these features of the data that make the special methods called survival analysis necessary. So you need a special technique. You can't just be using the normal techniques. So when we study survival analysis, there's something called censoring, which is very important. Because when you have the data you've collected, the data can be, they are censored. So most survival analyzers must consider a very important analytical problem called censoring. So censoring can occur in different ways. You have left censoring, right censoring, and you have, in the middle also censoring. So we say we have, now it is caused by not observing some subjects for the full time till failure. For example, you may have some people joining the study when they were already, when they came, they already had the disease. So you don't know when they actually were diagnosed with the disease. Or it may happen that some of the, participants just left the study in the middle. Now you don't know why did they leave, and they might have died. One person was died, but you don't know. Maybe later you'll get to know that the person died, but you don't know exactly when the person died. Here we have records for patients dying from breast cancer, but in some situations, it may not be possible to mark the exact time of death. The problem occurs when the patient dies in between, after the end or before the study, and hence censoring occurs. So there can be three primary reasons for this. Patient doesn't have the event before the study ends. Patient left follow-up during the study period, or patient died in the study period. So you have right censoring, and this is the one that's mostly used. The study ends, but no event is observed for some of the patients. Hence, true survival time is greater or equal to the observed time. It is the most popular censoring mechanism. It is the most one that used in most of the studies. So you have started and you end, the study end, but the that event hasn't. And left censoring, event has already occurred before the start of the study. True survival time is less than or equal to the observed time. This occurs when someone comes for a follow-up and first exposure is noted as an event. First time comes the study. Event, and then you have interval censoring. Event occurred somewhere between time T1 and T2. This scheme is applicable to both death and exposure to disease events, depending on which event you're actually studying. It is a combination of both left and right censoring with one limit as infinite. Now, how are survival data described? They're described and modeled in terms of two related probabilities. One is the survival and the second one is hazard. So the survival probability, which is also known as a survivor function, ST, is the probability that an individual survives from the time of origin, for example, from the time of diagnosis of cancer, to a specified future time event, which could be, recurrence of the disease or could be death. It is it's fundamental to a survival analysis because survival probabilities for different values of T provide crucial summary information from time to event data. Now, these values describe directly the survival experience of a study cohort, that is the survivor function, and the the hazard also, both of them. So they are like, two sides of the same coin. Now, survival function, we look at that first, and actually, mostly they describe it using some, a model called the Kaplan-Meier model. So the survival function returns the probability of an event occurring after a time T. Mathematically, the event could be death, but we actually, when we say survival function, we actually know, we want to know up till that time that the person survived. Okay. So survival function ST is equal to the probability that the person survives up till a specific time where T is greater than 0 up to infinity. Now, ST is nothing. Now, alternatively, it can be said that ST gives us a probability of a subject surviving after time T. So it's nothing but a probability distribution over time. It's the probability of survival to time. That is the probability of no event before time T occurring. Theoretically, it ranges from 0 to infinity. And of course, ST will have values from 0 to 1. So at the beginning, at time 0, it's 1. At time infinity, it will be 0. Okay, so at the starting time, it's 1, and you expect at the end, it's going to be 0. Ideally, survivor, that is a survival function, represented by decreasing smooth, it's presented by a decreasing smooth curve, which begins at ST is equal to 1, at time T is equal to 0. So in theory, it looks like this. But in practice, it will look something like this. So in practice, the curves generated from real data sets look more broken and stepwise. So the more patients you have, the more number of participants you have in your study, it will look smoother. But when you have less, it's going to be like looking broken like this. So the survival function. Now, one important feature of the survival function is that it is monotonically decreasing. As you can see here, it decreases. So we can say that S survival at time T1 is less than survival at time T2, where T1 is greater than T2. Means survival at time, let's say, for example, 20 months will be less than survival at 10 months. Survival chances from an event tend to decrease over time, of course, because we're studying, if we're studying diseases, we're studying, let's say, equipment, machines, after time, there'll be tear and wear in there also. So, it might fail faster. It's going to fail over time. So chances of surviving of a cancer patient from event death decreases as time passes, or even for the machines, like I told you. So what are the aims of doing survival analysis? I think many people already in clinical trial, they know what we use that very often. For example, to estimate probability of not experiencing an event of interest, like not dying, that is surviving over any given period of time. Or to compare overall survival experience between different groups of individuals. For example, you're studying a cohort of cancer patients. One group in that is being given one treatment, another one is given another treatment, and you're trying to see over time how do both groups survive. Okay, or it could be in a randomized clinical trial. Each group may be given different treatment or whatever. Or I'm going to show you an example whereby I have stratified the cohort into two groups based on harboring a mutation in a certain set of genes, which I know are supposed to be important in that cancer. So you can, split your group based on your interests that you're working. Now I'm going to first start to show the Kaplan-Meier estimation of survival function. And for that, I've taken, a sample data set from this paper. Okay, so if you go to that, you'll see there's data. I'm just taken 20 of that. So it's a non-parametric technique of estimating and plotting the survival probability as a function of time. And here we have the weeks. Okay, so over 6 weeks, for example, we note one death, then a second death at week 13, another death at week 21, and then so on and so forth. You'll read that. So based on that, so weeks to death or censoring in 20 adults with recurrent, this astrocytoma. In fact, we're going to have 2 of them. So when we're going to study it. So let's see how it works. Yes. These zeros and ones, the ones are death, zeros maybe they left. 0, 1 is 1 death, sorry, not 0, 0 death. At week 31, no death happens. So they have measured, sorry, they're measuring at different time points if there has been a death. So at week 6, there was 1 death. At week 13, there was 1 death. 21, there was 1 death. At 31, no death occurred. 37. So these are time points where they've measured different time points. So then at week 219, 1 death occurred. So they're looking at the death. But there are some weeks that they actually measured no death. So 0 means 0 death.
This is, the ID stands for different patients or?
No, they don't. No, they're not patients. It's just number. It's just a number of a table. Observation 1 to 20. Oh, sorry, there are 20 others here.
Okay, so these are different people and
20 others, and you're studying number of a period of time. Here it's up to 219 weeks. So you're looking at or maybe you're right. Maybe this patient number 8. No, it's not that.
Yeah. So may I come in? So,
yes, sure. Thank you.
So here we are trying to see the outcome as a time to event, right? So the weeks represent the time and the death. So death is a dichotomous outcome, whether event happen or we don't know, right? So for participant 1, it took 6 weeks to get died. And similarly for the participant 2nd, it took 13 weeks to get that event. But for the participant 5, you can see you have data till 31st, and you know that this participant did not get died. But after that, you don't know what happened to that. Yeah.
Yeah, that was I thought. The 0 means maybe the person has left the study, but you don't have the
Yes.
So
Event.
basically it's like,
It's a censoring.
It's censoring, yeah.
sorry, what is that?
Censoring. Left.
Oh, I see.
left
I
the
mean, you
study.
don't have the data, or
don't have the
you
data.
stop tracking that
Yeah, you stop
patient
tracking
after
that,
that
yeah.
point.
No, so you have a data for time thing, but you don't have data of event.
Yes.
So your time to event outcome consists two kind of variables. One is the time, another is the event.
Yes.
So you know the time part, so you have half information, but you don't know the event.
Exactly.
Okay.
Thank you. So how do we actually come to that survivor function? So we have those. So we're measuring at different times. Okay, 6 weeks, 13 weeks, 21 weeks, 30 weeks. So 31, you see, that's the point where you have this censoring. So all these 0, you have the asterisk there, means you don't know that patient wasn't there, must have left. So in that table here, you have the censoring. These are star. Okay. So let's say we have 20 individuals in the study at time t is equal to 0. And the first death at t is equal to 6 weeks. Okay. So no individuals censored before t is equal to 6. At t is equal to 6, one person died. So probability of death of each individual at that point in time is 1 over 20. So there were 20 participants, one passed away, 1 over 20 is 0.05. So what is the probability of surviving at t is equal to 6 is 1 minus 0.05, which is equal to 0.95. Or you could say 1 died, 19 was still there. None of them left, 19 was still there, 19 over 20 is 0.95.
Sorry, can I just go back to the table that was confusing everyone? And I wanted to, if it's helpful, just remind everyone, remember when I talked about the cohort studies? I don't know if you recall, I said that when you have something happening over time, you always have per person years, because you always have this time difference. And then I was also talking about the fact that people come into a cohort study and they may leave at a cohort study at different times. So for each person, time point 0 is when they get registered into the study. It may not be the same date for everyone. But the other point, and I think that's what we're looking at here, is people may be at one point in time when you want to see how many deaths there are. For each individual, they may have been in the study at that point for different lengths of time. So at this point of time when these data were taken, for the first person, the data was taken, they were 6 weeks in the study, and at that point they were deceased. Whereas the person, ID number 5, they've been in the study for 31 weeks and they're still alive. So remember that people aren't, at one point in time, people aren't necessarily in the study for the same length of time. They get enrolled on different dates. So I think that that's what we're looking at here, at however many weeks since that individual was enrolled, what is their status at that point? I don't know if that helps.
So this, I think this is probably the time is calculated from the day the diagnosis was made till the...
Whatever the entry point was to the study, yeah. Yeah.
Okay, so this is when the first death occurred at week 6. So this is the survival probability that we get is 0.95 at week 6. Then you have a second death occurring at week 13. So at week 13, at week 6, one person died. So we have 19 participants left, okay, at that point in time. So at week 13, another person dies. So 18 individuals in study between T13. I think so we have 19 here. Okay. So at week 13, there'll be one more person who's died. So 18 individuals will be left there. Okay. Between time 13 to, of course, to 21 to the next point. So probability of death for each individual at this point in time is 1 over 18. Is that right? Yeah, that's okay. It was 1 over 20. That should have been 1 over 18, 19, right? So 1 over 19, 1 over 18. I think I've missed one. I've missed one of the slides. Because I should have shown the week 13 also. Right? Or they did something, yeah, at week 13, one person died. So I should have shown the week 13. I think I missed one slide. Yes, I've missed that one. So at week 13, normally what would have happened, there were 19 participants left. So the probability would have been 1/19 for dying. And yeah, and we have to multiply that by the original probability for the first part here.
Ma'am, actually, I'm not getting why the survival probability always decreasing, because you're accounting interventions, right?
Yes.
So as a result of interventions, that may also increase the lifetime.
No,
of
no,
a
I'm not.
patient.
No. My event is not intervention in this one. My event is death. In
No.
this one is death.
Yeah.
Yes.
No, event is death, but
Yeah.
as a result of interventions, the life of the patient can also increase, right?
But I didn't say, I mean, they were in, I'm doing any intervention.
Okay,
I'm just
without
following.
interventions.
Yeah, I'm just following them in the study.
Okay.
So they might have got the intervention before and I'm following from that time. For
Okay.
example, it could be that they've gone some treatment and from that time I'm following them.
Okay.
Yeah, so I'm not saying that at that point in time they're getting some intervention.
Okay.
Yeah.
Suppose you are accounting right censoring.
Yeah.
So study ends and the person dies.
Yeah.
And because you are not tracking after the end of the study, so death can be because of any other reason, not just because of the cancer, right?
Yeah. So
Any other
actually, yeah.
comorbidity.
Actually, you're very right, because when we have the data for the cancer patients, we have different types of survival. So you have overall survival, you have disease-specific survival, you have progression-free survival, you have different kinds of survival. So then you depending on what study you are doing, you're going to use that data. So then for overall survival means the person dies for about anything, okay? But disease-specific survival will tell you that this person died with cancer. So
Okay.
yeah, you have different types of survival, like you said.
But interventions also should play role here, no? Like probability of death given this treatment, or probability of survival given this treatment.
No, right now I'm just considering one variable.
Okay.
Yeah, I'm just considering one way. I'm just looking at time, univariate. This Kaplan-Meier is only univariate.
But
So afterwards, when you're going to do Cox PH survival model, in that one is multivariate. So then you have multiple variables that comes into play. For the time being, when you were defining the survival function using the Kaplan-Meier is only one, as if I'm just looking at time.
Mm.
Yeah. So you have it. Actually, we don't use that. Actually, we use the other one.
Ma'am, I want to ask you regarding death as a criteria
Event.
for the survival, as a criteria for survival, because I guess just because of the death, you are getting the step function. Suppose in place of death, you are just measuring some immunological parameter that is continuously decreasing with respect to time. That would, I guess, be more better measure of the survival, right? Because death is itself discrete.
Yes.
And
So
if you have a continuous rate of decrease of the survival, then you can even get the same results even with the less sample space, right?
Yes, you're right. But actually, I mean, you're saying that you're measuring some other things, like instead of
Yeah.
death.
Yeah.
But the event, you're saying it is a binary variable. So
Yeah.
either there is death or there is no death.
Yeah.
Like it's dichotomy, there's only two possibilities.
Yeah. Yeah.
So this is what we're measuring.
Yeah. So in place of that, because death is discontinuous, either binary, like you said.
Mhm.
But in place of that, if we can measure some immunological, like the cells, how the cells are proliferating,
Yeah,
or
probably
that may be more continuous.
Maybe, but the survival analysis problem that we've studied is based on this one. So I'm sure there is other one, but I haven't looked at that one.
Can I
So
can
it's
I
about-
add?
yeah.
Can I add to what he's asking?
Yeah.
Here, the outcome is binary.
Yeah.
You can also have continuous outcomes in survivals. For example, quality of life. It is a continuous measure which decreases over time, or it may increase over time. But here, the example is talking about binary. You could have, but different models have to be fitted, not Kaplan-Meier or Cox proportional results model.
In that one, if you're just measuring that, it'll be just a regression, normal regression. Well, here we are measuring, we're actually looking at the time and the event. So
Yeah.
it's two. It's like, when I'll come later, it's like in a machine learning, where you're going to do machine learning. We've done classification with one variable, regression with one variable, but here it's a double variable.
Yeah.
So both of these variables come together as a target and outcome. So you have to have the event and the time. It's called time to event.
No, but if we can measure the quality of life, then that may be less confounding than death, right?
Some objectives may
Those-
be for death, some
Yeah.
objectives may be for quality of life, some objectives may be for disability. Depends upon what the researcher wants to measure. If the researcher wants to measure death, then this is more appropriate. If the researcher wants to measure quality of life, a different model will be applicable.
But here the researcher wants to know the survival due to cancer.
Survival means the outcome will be either died or alive.
So when we talk
Okay.
about survival, we're actually talking about the event. The event is death.
Okay. Yeah.
So if at a specific time t, the event hasn't occurred,
I see.
so the person has survived.
Yes. Yes.
So this is what we're measuring.
Mm.
So when we are going to look at from the other side, then it becomes hazard. So you have the same thing. You can look at it from the hazard function and the survival function.
Okay. Thank you.
Yeah. So I think in 1 week I've missed. So normally at week 13 also there was one death. So at that point in time, you would have 19 participants left, and out of the 19 participants, one died. So probability of dying at that point is 1/19. So because we have already had one death before, so you'll have to multiply the original probability by this one. And then for the survival, you'll have to subtract the combined probability from one. You would have got that. So that one I think I've missed. So then we come to week 21. So if two persons have died, one at week 6, one at week 13, so you have 18 participants left in there. Okay, so 18 individuals that study at t is equal to between 13 and week 21, where you have the next event occurring. So probability of death for each individual at that point will be 1/18, okay, which is 0.056. So probability of surviving beyond this week, 21 is 0.9 for the original that we calculated. There's 1 week that I missed, one participant. So when you multiply those probability, we got 0.9. Multiply by 1 minus 1/18. So we get 0.85 now the probability of survival. So you can see that probability of survival will keep decreasing. So 17 individuals in study between 21 and 30 will be left because 3 participants have died. So probability of death for each individual at week 30 will be 1/17, which is equal to 0.059. Probability of surviving beyond the week 30 is, we already had 0.85 calculated there, multiply by 1 minus this, which is 0.8. So you can see the probability is decreasing gradually. Okay. So if we take, so this is here, my slide went up and down, should have been here. Sorry for that. I'm going to correct it and do that. So the next one is week 31. So at week 31, we have 16 participants, individuals left in the study between 30 and 31, so between that 1 week. And one individual censored at week 31. Remember, there was a star, so left the study. So probability, now we don't know whether the person died or the person just left the study. Okay, so for us, it's a censoring. We're going to count it as one participant left from there. So probability of surviving beyond week 31 remains as 0.8 because we don't know what happened. Now, 15 individuals in the study between 31 and 37 are left. Probability of surviving beyond the week 37 is now, we already had 0.80 from before. We multiply by 1 minus that one person dying over the 15, which is 0.747. So now the probability has decreased to 0.47. So if we continue like that, we'll see a graph like this. The probability decreases as you go over time. Okay. So first death, t is equal to 6, survival probability is 0.95. Second one, t is equal to 13, survival probability is 0.90. And third death, t is equal to 21, survival probability is 0.85. We can continue with that, and we can get this, Kaplan-Meier plot drawn in a stepwise fashion like this. Okay. So this is one, that is, we're just studying the whole cohort as it is. But of course, in many applications, we stratify, the group into, the whole cohort into different groups based on different treatment, based on different, maybe like genes or different subtype, like you have the cancer for the breast cancer, there were 5 subtypes. So based on subtypes, so you're going to stratify your patients on that. So now let's say we have only 2 groups here. So for the same study that we took from there were 2 types of, cancer. One was astrocytoma and the other one glioblastoma. The survival chances appear better when you look at that. I've taken it from the paper. It looks like if you look, how do we read that? So you can see, for example, at time 104 weeks, for this group, the group in this one, the glioblastoma is, let's say at 104 is somewhere between, 0.2 or something, less than 0.1, 0.08 or something. And then for the other group, astrocytoma, it's more, 0.2. So we can say that survival chances appear better in the individuals who are in this group with glioblastoma compared to this second one, but is difference between groups statistically significant? So, I mean, can we say that this is true? Is it significant, the difference between these two? So for that, we need something else, which is called the log rank test. Okay. So comparing two samples, when you're comparing two groups, could compare median survival time or probability of surviving up to any particular time. So we have to use a test which compares survivors over a whole follow-up period. Now, we use a log rank test. This tests the null hypothesis that there's no difference between these two groups. And this, I think, they explain on the first day, the hypothesis thing, hypothesis testing. So log rank test statistics is based on calculating the expected number of events that could occur under null hypothesis at each event time and comparing to observed number of events. And this is done under the null hypothesis. It has a chi-square distribution and 1 degree of freedom. This is statistics, and my disclaimer, I'm not a statistics person, and these things I think have been taught in the first day. So let's say we have this group again. Now we have, from the same paper I've taken that, we have two groups of patients, one from Astro and one from Glio. Okay. And let's say at week 6, so there now we have taken 51 participants total. You have 20 in this group and 31 in this group. Okay. And we see that at the end of the study, this one has 14 deaths, this one has 28 deaths. So let's say in week 6, I'm sorry, this thing is appearing here. So 1 death occurs in the group of Astro. Okay, in this group. My online thing is appearing. Just disappears. Showing it to the room. Yeah, so you can see at week 6, 1 death occurred in this group of patients. So there were total 51 patients. So 1 patient died out of 51. So what is the probability here is that, so total we had 20 participants in this group. So 20 over 51 multiplied by 1 because 1 patient died. While here you have 31 over 51. So calculate that, you will get this one. Now at week 10, in this group, no death happened. In this group, there was 1 death that happened. Okay, so it will be, up till now, you have 2 patients that have, no, there were 2 deaths. 2 happened here. So 2 over 50, not 1, there were 2 because week 10, we have 2 deaths recorded. So 2 over 50 because 1 passed away out of 51, 50 were left. Now we had 19 left in this group. Okay, there were 19 left in this group. So 19 over 50 multiplied by 2, we get this. And here we get, 31 over 50 multiplied by 2. So you can continue like that. This is just for demonstration purposes. So the log rank test compares observed number of events, say OI, for cancer type I to the expected number by calculating the test statistics. It's it's normal chi-square distribution. This value is compared to this distribution with G minus 1 degrees of freedom, where G is the number of groups. In this manner, a p-value may be computed to calculate the statistical significance if you're using 95% confidence interval. So you're going to use 0.05. If it is less than 0.05, then we can say that whatever we got in this one, like here, if we see the difference, and with the log rank test, normally it should give that. If it's less than 0.05, then you can say that it is significant. So the log rank test unlikely to detect a difference between groups if survivors cross over during follow-up. They cross over. It assumes non-informative censoring. I mean, all of them have the equal, of being censored or dying or whatever. Can be extended to compare more than 2 groups, but only provides a p-value, not an estimate of the size difference between groups or a confidence interval. So now survival function, we will look at the survivor function. Sorry, survival, when you actually look at the chance of surviving, the probability of surviving for a patient. Now, conceptually, there's something known as hazard function, which is the opposite of survival. So it is the event rate or death rate. However, it's opposite, but it's not the probability, it's a rate in this case. In case of analysis of impact of diseases on humans. It can also be termed as a failure rate if you're looking at equipment. Hazard is a probability that an individual who is under observation at time t has an event at that time. So hazard function is represented as follows. So you'll see here that something happened between t and t plus delta, where delta is very small. Within that short span of time, an event occurred there. Okay, where delta must be very small. The event should be occurring in a very short time, between t and t plus delta. Delta must be very small. So mathematically, that's the formula. So the hazard function and the survival function, like I said, they are the two different sides of the same coin. Hazard at time t is the potential per unit time for the event to occur, given that the subject has survived till the time t. Basically, it's a rate of event at time t. It is clear from the expression and definition that hazard is a rate, okay, rather than a probability. Hazard and survival function are just two ways of specifying a survival distribution. So either you can use a survivor function for the survival, or the failure, you use the hazard function. So this is a relationship between these two. Now, how do we analyze the relationship between the survival and the hazard functions? So survival, we actually saw it's like this. Survival at time t is equal to the probability that the person has lived up till time t. And it is, we can also, if we say probability that t is greater than small t, we can also say that this is 1 minus probability t less or equal to t. Now, probability that t less or equal to t is also known as cumulative risk function and denoted by ft. So we can say that ft is equal to, if st is equal to 1 minus probability of t less or equal to t, or we can say 1 minus ft. So we can say ft is equal to 1 minus st. We just rearrange the formula, we get ft is equal to 1 minus st. So from theory, we know that probability density function, when you do probability, denoted by ft, is a derivative of distribution function. So we can say that ft is equal to d by dt of this capital ft. Okay, so which is 1, and this is also equivalent to 1 minus st. So 1 minus st, and of course d by dt of this is 0 minus d of dt of st. So it's the negative derivative of the survival function. So density function is a negative of the derivative of survival function. From the previous equation by the theorem of conditional probability and omitting the suffix t, we get the expression of hazard function as ft over st. Hazard function is equal to ft over st, survival. So basically, the hazard at time t is a probability that an event occurs in the very short neighborhood of the time t, like the delta is very small, divided by the probability that the subject is alive at that time. So hazard being a ratio of two probabilities, it is a rate rather than a probability itself. So when we talk about survival analysis in machine learning, we will normally have hazard ratio also that we use to actually, do the evaluation. So unfortunately, unlike the survival function, survivor ST, there's no simple way to estimate HT. Instead, a quantity called the cumulative hazard function is commonly used. The cumulative hazard function is a total hazard from 0 to time t. Okay, so if the total, you can also write as an integration. The formal relationship between cumulative hazard and survival is given by this. ST is equal to e to the power minus HT. So when we are doing our survival analysis algorithms, sometimes you have to measure the survival. Sometimes you want to report the hazard ratio also. So you have to know this, relationship between these two. So hence survival and hazard are both functions of time t. It seems like, up till now, it seems like survival probability of a subject is dependent only on time. And it looks like it's only a univariate model up till now. So based on the Kaplan-Meier, it looks like it's just a univariate model. But we don't only use the Kaplan-Meier model. We use the Cox proportional hazards model also. Okay, so one of the most popular algorithms that we use for survival analysis in machine learning is the Cox proportional hazards, and there are different flavors of that. So this was proposed by Cox in 1972 with no assumption on the H naught t, what happens at time 0. It is easy to implement, takes covariates into account, and provides interpretable results. It's a semi-parametric method that aims at modeling the hazard function. That's why it's called Cox proportional hazards model. It makes a parametric assumption concerning the effect of the predictors on the different variables that you use in there. but makes no assumption regarding the nature of the hazard function, HT itself. And this we have already seen, so we're just going to take that. So it's represented as follows. So instead of H, I've taken here with lambda, it's the same HT at time, HTX is equal to, you have a baseline hazard at time T0, and then you have the hazard ratio as such. And these are the different variables in the study. So you have coefficients for different variables, okay? Or we can also write it as follows, HT is equal to H naught T times EXP. The model consists of two parts, the baseline hazard, it describes how risk evolves through time, and the hazard ratio itself, the whole thing here together, it models the effect of the explanatory covariates on the risk. So all the variables that you're going to use could be gene expression, gene mutation, etc., etc. So with this semi-parametric function, the model relies on a strong proportionality assumption. For example, if a patient has a risk of relapse in initial observation that is twice as low as another patient, then for all subsequent time observation, the risk for that initial patient, the first one remains twice as low compared to the other one. Now, application of Cox-PH model, the outputs of the model are highly interpretable. At the instance level, the model provides for each observation a risk score. The higher the risk, it is more likely that the patient will die. A survivor function, it enables analysts to assess the probability of surviving at least to a point over time, and the hazard function. And then at the global level, the model can be explained through coefficients for each of the covariates. A positive coefficient indicates a worse prognosis, and a negative coefficient indicates a protective effect of the variable with which it is associated, these coefficients. For a positive coefficient, the higher it is, the stronger the impact on the relapse or the death or whatever. So let's consider the prostate cancer data set from the TCGA, the Cancer Genome Atlas. It is the biggest publicly accessible database for cancer data. Okay, I've taken it from there. In there, you have 494 samples of men with prostate adenocarcinoma, and it has data for gene expression, mutation data, and protein expression data. So using all these three data, we have done a survival analysis on that. But I have actually stratified the cohort into two. So based on, there's something called the androgen receptor, which is that pathway is very important for prostate cancer, progression. So the androgen receptor is a member of the hormonal transcription factors. The expression of the androgen receptor protein and its activation by male hormone and androgen are fundamental to prostate development during pubertal and malignant transformation during later ages. So there are 19 genes known to be downregulated by androgen receptor in PCA. And due to that, this could be causing, an onset or progression of the disease. So these are the 19 genes. So I chose these 19 genes, and then I stratified the group. So you can, and I have actually studied the progression-free survival for those patients. And these are real data sets collected. And when you look at that, you can see that you have the altered group and the unaltered group. Altered group means this group have mutations in those genes, pathogenic mutations. Now, mutations can be pathogenic and non-pathogenic. Pathogenic means actually it's going to translate into some protein expression, which could be either increase something that's not supposed, like cell cycle is going to increase, which is not supposed to be done at that rate, or maybe it could actually affect a tumor suppressor, something that's a guarding cell, and that stop working. So basically, it has some pathogenic mutation, which has some effect afterwards. So using all those three data, mutation, gene expression, and protein expression, and the clinical data also, this is what we got. So now disease-free, it's disease-free survival. Now, what is disease-free survival? It's defined as a length of time after primary treatment. The primary treatment could be, the different treatments, chemotherapy, radiotherapy, or other therapies that we do in the prostate cancer patients. After that primary treatment for the cancer ends, that the patient survives without any signs or symptoms of that cancer for a period time T. So if you look at this, for example, if I look at about 50.73, somewhere around here, 87.87% event-free survival in unaltered group, it's higher. While for the same, at the same time period, for the altered group, it's 70.86. So it's about 17% less in this one. So definitely there's a difference. So we could say that these genes, these 19 genes, play a role into, you know, the disease reoccurring after the treatment. So, and when we look at it, it also generates a log rank test, which is p-value is equal to 0.0267. So if we're considering the 95% confidence interval, we could say that potentially there's a significant difference between these two groups. So this one I actually did it online on a web resource where the data is found. But I'll show you how to actually do it using Python and other libraries also in a while. Okay. So how is machine learning now leveraged for survival analysis? I gave you a brief introduction, very brief introduction to that. So now the Cox-PH model, I already explained how it works. So we have that model in different libraries. So there are two libraries that we use in Python. One is called the sklearn survival model, and then we have the lifelines, SK survival library and the lifelines library. So we have the algorithm for the Cox-PH model itself. There are different versions of that. And then we also have random survival forest model. Just as standard random forest, random survival forest in a training consists of a number of survival, it's an ensemble method, survival trees, okay, of the data set and using averaging for more accurate prediction and limited overfitting. The main difference lies in the metric used to assess the quality of a split, compared to the normal random forest that we have. And here, so here is a log rank, which is typically used when comparing survival curves, among two or more groups. Then there's another one, gradient boosting survival model also. This, when applied to survival analysis, is also very similar, like the Cox-PH model and the other one, the random survival forest. Consider a combination of, or combining in additive manner the predictions of multiple base learners to obtain a powerful, overall model. So we have gradient boosting classifier normally and regressor also. So we also have the survival one. The base learners are also called weak learners, often very simple models which you can integrate together. It differs from random forest as the survival trees are not trained independently but sequentially in a greedy stage-wide fashion. Then we have survival support vector machine model. And this one is again similar to the support vector machine that we have normally for regression or classification, can be extended to survival analysis. This is also a very versatile model as it can account for complex nonlinear relationship between features and survival via so-called kernel tricks. However, its predictions cannot be easily related to standard quantities, that is the survivor and the cumulative hazard function. Now, how do we compare these different four models that we've looked at? So there's, when we compare the survival analysis models, what are the metrics that we use to say that this is a better model than the other one? So there's one that's called the concordance index. We call it C index. The most frequently used evaluation metric is the C index. It measures the capability of the model to provide a reliable ranking of survival times based on individual risk scores. It is computed as a proportion of concordant pairs in a data set. If you're actually looking at two observations, first, to be comparable, the observation with lower time needs to have experienced the event. Second, if comparable, it is concordant if the risk estimated by the survival time is higher for individuals with shorter survival times, which makes sense, of course. Now, cumulative, or we can use the dynamic AUC. You've seen the AUC, area under curve we use for the classification. So here you have the dynamic AUC. You do it over time. So ROC curve is extended to censored survival times. The idea is to consider several points in time. At each point, we consider separately the cumulative cases and the dynamic controls. All individuals in the cumulative cases who have experienced the event before or at the time that you're measuring, individuals who will experience event after time t. We can then evaluate the model and its ability to distinguish subjects who will experience an event over time. So sensitivity from those who will not, over time sensitivity, and the other one is specificity, just like we have in normal, machine learning models. So finally, to actually be able to conduct survival analysis, there are some key requirements. The first one is uninformative censoring. That is, censored individuals, because of loss to follow-up at a given point in time, should be as likely to have a subsequent event as those individuals who remain in the study. Secondly, the length of follow-up. You need to have enough time. Time to event studies must have sufficient follow-up to capture enough events, and therefore ensure there's sufficient power to perform that. You can't say that I'm going to follow the patients over 2 months, okay, and then I want to do that. Completeness of follow-up, each patient who does not have an event can be included in a survival analysis for the period up to the time, at which they are censored, right censored, but completeness of follow-up is still important. In general, disparities in follow-up caused by differential dropout between arms of a trial or different subgroups in a cohort study need to be investigated. Then cohort effect on survival. In survival analysis, there's an assumption of homogeneity of treatment and other factors during the follow-up period. For example, you may have a number of patients or number of people enrolled in a study. And at the beginning, you had some which were supposed to be diseased and some which were not diseased. Over time, it may happen that those who are not supposed to be the disease, they become diseased. They change from controls to become cases. Okay, so this might change. But in a long-term observational study of patients of cancer, the case mix may change over the period of recruitment, or there may be an innovation in treatment that you're actually giving. That also might change. Also, finally, between center differences in a multi-center study, it is important that there is consistency between the study methods in each center. So if you have all these, then you can go forward with a survival analysis. Okay. Now, I'm going to show you an example run of a survival analysis using a data set, which is called the Haberman data set. That also I've got it from Kaggle. The dataset contains cases from a study that was conducted between 1958 and 1970 at the University of Chicago hospital on the survival of patients who had undergone surgery for breast cancer. Okay, so you can get that. I'm going to share this with you afterwards. How does it look like practically? Of course, you have everything, the data description, the rest of the things will be the same way. You mount your drive. You read the data, and you can see here the data. So the data I'm going to share with you, in the data, you don't have 1964, you have 64, 62, 65. So I've added the 1900 to get the actual year, because it's shown as 62, 65. Connect this. So in classification, you have a class as a target. In a regression, you have a quantity. In a survival analysis, you have 2 columns. Okay, so the will be the time. Okay, you'll have the time and the survival. So here, let's say you have this, you call it year, whatever the time. You'll have 2 of them that you're going to use. So normally this is just a kind of a toy example, but the data set I've given you for the TCGA female breast cancer, in there you have survival in month, and then you have the event itself. Person has died of disease or not of disease. Okay, so you do that, you'll see this. So I'm going to use a library called Lifelines. So this is not installed in Google Colab. So I have to install that. So I'm using age actually as the I'm using the age as a time variable here, and I'm using the serve as the event. So basically, when you look at the data, you'll have here the age and so this is my my class survival, 1 or 0 you'll have here, and this is my time. So I need to have a time feature and I need to have an event feature. So I'm using the age as the time and the serve as the event. So then what I'm doing is that I'm importing the Kaplan-Meier feature from Lifelines. Okay, import that. And then I'm going to create an object of type Kaplan-Meier here. Okay. And I'm going to fit that with the time and the event. This I'm just giving that. So it's going to plot it. Almost done. So you'll plot it, you'll see the plot here. And of course, it's like a decreasing one. And then monotonically decreasing plot. And then now I'm going to actually do, instead of, I'm going to use the same, I'm going to create the same plot, but I'm going to, divide the group into two. Okay. So I'm going to divide the groups based on the number of, NB post detected. So this is my variable here. I'm going to create two groups. One where it's greater or equal to 1, and the other one's less than 1. So I've got two groups. And then again, I'm going to fit the, I'm going to have, fit that with the time and the event. Okay, and I'm going to plot that. So I'm going to use it for both groups, and this is how it will look like. So you can see that the first one I've got at least one positive axillary detected, and the second one no positive nodes detected. So you can see the no positive one will have a higher survival probability when you look at it as compared to one that has at least one positive one. So this is just a Kaplan-Meier for visualization. But normally, if we want to actually do the survival analysis, now why do we do survival analysis? We want to, for example, know which features actually are going to correlate with my event. Okay. So for example, if I'm studying, let's say, want to know what is among different cancer patients, what are the mutations or mutations in genes that could be actually, causing the early death of patients. Okay. So then I'm have to find those features of the gene. So I'm going to get the best, normally we say the signature, the gene signature that actually correlates with the survival. So this is what we're going to do. But in this case, I don't have genes. I'm just going to use, the 2 or 3 features that I have there. So I'm going to use a Cox pH fitter I'm going to import that from the Lifelines library. I'm going to create that. And then I'm going to have my data. And I'll say that time is age. So this one is for time, for the time feature, the T. And for the event it's served, I'm going to just say the event is served. So from the data table, I have the fields age and serve I'm using as my target. For survival, I have like two columns that I use as my target. And I'll fit that and I'll print the summary. Okay, so I'm going to print the summary of that model. Okay, so it's going to give the different, coefficients also for that. So you can see the coefficients for each of them it's giving. So there are only 2. There are only 4, I think, columns in the data. 2 of them I've used as the target, and there are only 2 left. The NB detected and the operation here. So these 2. So what are the coefficients for that? Okay, these coefficients are different, level. You have the values for them. And remember that formula, you have the baseline value, and then you have the hazard ratio, the second part where you have for each of the covariate, you have the coefficient. So this is what it's giving. And so when you plot it, this is what there are only 2. So you see 2 of them, only 2. So you see 2 bars. So if there were 20, you would see 20 bars. So you can see which one has a higher coefficient, this one. Number of NB post detected. So it looks like this one actually contributes more to the event. In this case, my event is the death of the patient or whatever. Okay. So the summary statistic above indicates that the significance of the covariates in predicting the survival risk. Both features play a tiny significant role. However, you'll see that this one plays in. This has a higher. So this is a very simple, model for the survival analysis. But of course, I've given you a bigger data set. So you can practice that one in your own time using this template that I'm going to share with you. Okay. So you can use that. Just some, I actually want to prepare the notes for these presentation based on these materials. So I'll put it there. You can actually go and look at it more. And I've taken some slides from another presentation, which I've actually acknowledged. And I've also listed some very interesting articles. So you'd see there's a series of survival analysis. There's part 1, part 2, part 3, part 4 in the series, which explains, starting from the basics of survival, then it goes to the other parts. So if you want to learn more on that, you can read on that. There's another paper, so a primer for the clinician scientists. These papers are very interesting for survival analysis. And lastly, I would like to acknowledge my employer for granting me leave to attend this, the FCI for supporting my cancer research activities, and of course, I would like to thank ICTS for funding my trip and inviting me here. So that's all. Thank you very much. So again, I'm not a statistician, I'm not a clinician. I'm a computer scientist by training. So, I work with clinicians and epidemiologists and all. So, I can only answer the computing questions.
Yeah, questions? We had a few during the talk, but.
So I'll share the
Yes.
the slides and the notebook. So that notebook with the data.
Yeah, so, okay, let's thank Shakuntala and break for the evening. Also, you would have received a mail from the program office. I think the 9 o'clock session with Saurabh will be on Zoom on your personal device, not here. We won't be able to set it up here at that time. So, okay, so see you either online at 9 or tomorrow.
I'll share the slides afterwards. I've shared all the notebooks, including this one also, and the data.